What is coherence? Well, let's keep things simple again, okay? I would like to define coherence as that property that makes it possible to observe wave-like phenomena. Now, you can understand that, first of all, by saying that we are surrounded continuously by waves like light or sound and so on, but we do not observe phenomena like diffraction or interference very often. Okay, one exception could be a soap bubble in which you can see the beautiful colors that are coming from wave-like properties. Why is this? Why are not we observing in everyday life this wave-like phenomena? And the answer is that a wave must also possess this property that we call coherence. In order to better understand this, you can use any kind of phenomenon of this class, like for example, the diffraction by a pinhole. Okay, this is a screen, this is a pinhole, and we start here from an extreme case in which you have a source with only one wavelength, and it is a point source that is a source with infinitely small size. Now, in this extreme case, you always get coherence, full coherence. That is, you always see a diffraction pattern. Things are changing when you start relaxing these conditions, and we'll discover two aspects in coherence. First of all, if instead of having a single wavelength, like here, you get a wavelength band, then you may discover that you no longer have a visible diffraction pattern. And this is what is called time coherence or longitudinal coherence. Second, if instead of having a point source, you have a source with a finite size, once again, you may discover there is no pattern anymore. And so you have a second kind of coherence, which is called spatial coherence. It's quite easy to understand what are the conditions for these two kinds of coherence. First of all, for longitudinal coherence, let's take the phenomenon. So if you take two different wavelengths, each wavelength is going to give you a different diffraction pattern. Then you add all the other wavelengths in the band, and altogether you may find that the superposition of the patterns is blurring everything out. So you get a blob, you don't see anything, okay? Now, if you're looking at the distance between two fringes, you find in elementary optics that this is the distance, which is given by the distance between the pinhole, the detector, and the wavelength, and the size of the pinhole. So if instead of having one single wavelength, you have a band of wavelength, this distance is going to be blurred by this. And so, very simply, you don't see a pattern if the blurring is more than the distance, okay? And you plug the condition and you get very simply delta lambda over lambda smaller than 1. That's, by the way, why you see the colors of soap bubbles, okay? Because with your eyes, you take the radiation, the sunlight, and you find the eye is filtering, so the delta lambda is going to be the visible range, and this is almost automatically fulfilled for visible light, and so you can see the colors of soap bubbles. You can express the same condition by using what is called the coherence length, which is this quantity, and so you get time coherence. The coherence length is bigger than lambda. So much about time coherence. Okay, and second, about spatial coherence. I'm not going to go into the details here, but once again, you can imagine that each point of the source is giving you a different pattern, but the combination may give you a blob. So if you work out the conditions once again, you can find very simply that the condition to still see a pattern is this one, that is the size of the pinhole much smaller than this combination of parameters. Now you can look at the same condition in a slightly different way, which is also quite interesting. Okay, it is suppose that the source, as is shown here, is emitting over a solid angle omega. Now you realize that most of the radiation is not participating to diffraction because only the portion that goes to the pinhole is giving you diffraction. And so the active radiation is a fraction of the total, the fraction being essentially the ratio of the two solid angles, and this giving you this one here after you plug the condition. So you get to this parameter, which is called the coherent power factor, and you can express the condition for spatial coherence by saying that a source has this kind of coherence if it has a large coherent power factor. So these are the generic definition of coherence. Now let's go to X-rays and synchronous radiation. So what is the situation? That's the summary. First of all, we need a large coherence length, and second, you need a large coherent power factor. You look at these two parameters, and there is something that catches your attention. In both cases, you have a lambda square, which means what is easy for large wavelengths becomes beastly difficult if you go to short wavelengths. That is why you had in optics, invisible optics, this kind of phenomena for centuries, but in X-rays, we discovered them only pretty recently, and it was a good discovery, okay? So this is the first point. The second point is that if you go back to the definition of brightness, you realize that the same geometric parameters that give you a high brightness also give you a high coherent power factor that is large spatial coherence. So we got a bonus because we've been struggling for decades to improve the brightness by improving the geometry, and in the end we discovered that also got a spatial coherence. Since we have not been thinking about coherence for a long period of time, the X-ray scientists did not know very much about this aspect, but then all of a sudden we found that this source was not only good because it was intense and so on, but also because it had coherence. And now there are a number of techniques that are using coherence. Okay, I'm trying to keep track of the time because of the delay. I will try to